Right, hi everyone. So this talk is on the topic of Traffic Engineering 2.0. So what I'll be doing first of all is talking about segment routing or SPRING. I'll be giving an introduction to it, what are the fundamental building blocks such as adjacency labels and node labels. And then we'll go on to the second part of the talk, which is the NorthStar SDN controller. When it comes to a segment routing deployment, if you want to do segment-routed traffic engineering, for almost all of the use cases, SDN controller is pretty much mandatory. So we'll be talking about how NorthStar can do path computations of segment-routed paths and install them into the network. And then finally, if there's time at the end, we'll talk about telemetry, how we're having the ability for the NorthStar controller to consume streaming telemetry coming from the network and using that to drive change in the network. So that's a step towards self-driving networks, in fact. So let's have an introduction to segment routing concepts. So segment routing regards the network as a series of topological subpaths or segments, to give it a more snappy title. And you can steer packets through the network by sending it potentially through a concatenation of different segments in the most general case. And this slide shows an illustration of that. And so this slide shows several different types of segment, just to give you an idea of the different possibilities. And let's have a look from the point of view of router R1, which wants to send traffic to router R7 on the right-hand side of the slide. And suppose for some reason that, first of all, we want the packets to go to router R2 via the shortest IGP path. And then we want the packets to be launched onto this orange traffic engineered LSP, LSPX. And when the packets emerge from orange LSPX, we want the packets to be steered onto that blue link towards R6, and then finally onto that red link to R7. And we want to be precise about that. We don't want the traffic to follow any other path to get from R5 to R7 for that final part of the journey. And so we can achieve that by using the appropriate types of segment. And so in order to make the traffic go to R2 via the shortest IGP path, we use a node segment associated with R2. And so R1 knows that if it puts a particular MPLS label onto the packet, 302, then the next router in the chain will forward the packets along the shortest path towards R2, and each router will do that hop by hop until the packet arrives at R2. When the packet arrives at R2, it places it onto the orange LSP. And the reason why it does that is that the next label in the label stack that R1 had put onto the packet was label value 183 that R2 had advertised as being associated with this orange traffic engineered path. And then when the packet emerges at R5, the label 555 is exposed, which is a label that R5 had advertised as being associated with that blue link. And then finally, when the packet arrives at R6, there's label 718 on top of the packet, which tells R6 to send the packet towards R7. And so, as you can see, by virtue of the label stack that the ingress router has pushed onto the packet, that's defining the sort of sequence of segments that the packet is following through the network, and hence, defining aspects of the end-to-end path with different degrees of precision. So the node label just says, just follow whatever's the shortest path. The adjacency labels are sort of nailing the packet to a particular link. The so-called binding label associated with that orange LSP, steers the packet into that particular orange LSP. And so that's why sometimes it's called source routing, because it's this label stack that's imparted at the ingress that determines the fate of the packet as it propagates through the network. Now, terminology, segment routing is the most common name for this. Sometimes people call it SPRING because that's the name of the associated working group in the IETF. And if you're wondering what it stands for Source Packet Routing in Network ING. So we've got a G at the end just to make it more pronounceable than SPRING. So it's like a contrived acronym. So looking at some of these sort of mechanisms in a bit more detail, let's have a look at the adjacency label, which I alluded to. And so what happens is that each router, it has its IGP adjacencies with its nearest neighbours, and normally, it announces the existence of that adjacency and associated attributes. And when it does that, it announces an extra piece of information. It announces a so-called adjacency label. And so R1 says in its announcement, I've got an adjacency with router R2, and the adjacency label, the MPLS label that I associate with this, has a label value of X. And all that means is that if a packet should arrive at router R1, a data plane packet with top MPLS label X, that immediately tells R1 to simply pop the label and forward it on that link towards R2. So it's got strict forwarding semantics. And based on that, we can make a traffic engineering scheme. So in this slide, what I'm showing is the adjacency labels that each router has announced, and they're shown in these blue sort of call-out flags. And every router in the topology is aware of these labels because these are all flooded via the IGP. And so every router in this topology will have this sort of map in its mind. It will have all this information in its ISIS or OSPF database. Now, if we think about router R1 at the top left, suppose it wants to send traffic to R5, not via the shortest path, but via this particular path shown in red. It can do that by pushing the appropriate stack of adjacency labels onto the packet. And so if you've got n links in this end-to-end path as shown in red, then in fact you need n-1 adjacency labels to precisely specify this path. You don't need a label for the first hop because the router simply pushes the packet out on the required links. You don't need a label associated with that first hop from R1 to R2. So if we look at the label stack in a little more detail, what R1 needs to do is, because R1 wants the packet to go from R2 to R3, R1 must put in the label stack the adjacency label that R2 has advertised for its adjacency with R3. And that adjacency label is highlighted in red, and you can see in the diagram it's labeled 203, and so that's the top label that is pushed onto the packets that R1 pushes out towards R2. Now, once the packet gets to R3, R1 actually wants it to go on the link from R3 to R7, and so it looks at what that adjacency label is, and that's 552, and so that's the second from top label in the packet that R1 is pushing. And similarly, you've got labels for each of the other hops. And what's happening in the forwarding plane is that as the packet propagates hop by hop, each router is popping the topmost label and sending it on the corresponding adjacency. And so R2 sees that the top label's 203. It knows that that means it must pop the label and send it towards R3. R3 sees top label 552, pops the label, sends it towards R7, and so on. And so R6, it sees the final label, it does a pop of that label, and so you're just left with the bare underlying packet, because of this penultimate hop popping, and that's sent to R5. And so in this way, as you can see, we've managed to steer the packet through a precise sequence of links by virtue of the stack that's been pushed onto the packet, this stack of adjacency labels. And so what we've achieved is a type of traffic engineering. The interesting thing is that this LSP, inverted commas, only exists in the mind of the ingress router. So these of the routers in the path aren't explicitly aware of the existence of this LSP. All they're seeing is, adjacency labels which they're popping and, pushing the packet on its way. So that's, how we can achieve traffic engineering using adjacency labels. Now let's have a look at a different sort of label, which is, node segments. This is achieving something different, actually. What this is doing is it's actually saying we want packets to be sent towards a particular destination node with MPLS labels using shortest path forwarding. So we're not being precise about steering the packet along a particular sequence of links. We're not doing traffic engineering. We just want the packets to follow the shortest MPLS path towards the destination. Now, if you look at this diagram, in this diagram, in fact, all the IGP metrics are equal. And so if you think about traffic destined to R7 on the right-hand side of that slide, those green arrows show the shortest path tree as defined by the IGP. So if R2 is sending towards R7, it sends it to its nearest neighbour R3. If R4 is sending towards R7, it would send it to its nearest neighbour R5 and so on. So you've got this sort of inverted tree rooted at R7. That's just the IGP, SPF tree. Now suppose R1 does want to send packets to R7 using the shortest IGP path. What it does is it puts the appropriate node label onto the packet. This is a label that's associated with destination R7, and in particular it's the label that its nearest neighbour towards R7 associates with R7. And so I'll tell you how this label is calculated. What each router does is it advertises a so-called index. This is a number which is unique to that router, and that's flooded in the IGP. And in this diagram, the index is equal to the router number just for convenience. So R7 advertises an index 7 associated with itself, associated with its loopback address, typically. The other thing that each node does is to advertise a label block. And so this label block is the block of labels that the router has assigned for packets arriving at it, or transiting through it, which it uses for this shortest path forwarding. And so by way of example, R1, it wants to send to R7 using the shortest path. It identifies its shortest path neighbour towards R7, which is router R2. And so what it does is it says, okay, what's the label block that's been advertised by R2? Because these label blocks are advertised in the IGP. And this label block is from 500 to 599. And what R1 also needs to know is the index of the final destination route, which is R7. And so it adds this value of 7 to the value of the label block of the nearest neighbour router. 500 plus 7 equals 507. And so that's the value that's put onto the packet. Packet arrives at R2. R2 knows that this is the label it associates with shortest path forwarding towards R7. And so it says, who's my nearest neighbour towards R7? It's R3. What's the label that R3 is expecting? It's the label block that R3 is advertised, starts at 400. I add the index of the final destination router. 7 plus 400 equals 407. So it changes the label to 407, pushes it towards R3. R3 recognises that label as being associated with shortest path forwarding towards R7, pops the label, run the penultimate hop, so it just sends the bare packet towards R7. And so in that way, we've achieved shortest path forwarding using MPLS labels to a destination in the network. Now you might say, well, hang on, LDP has been doing this for the last 20 years, so why do I need to use this instead? LDP achieves a similar thing, shortest path forwarding using MPLS labels. The difference here is that you don't need an extra protocol. The IGP, which you always need an IGP, is distributing these pieces of information, the label ranges and the indices, and so you don't need to use LDP at all. Also, it gets you away from having to deal with LDP IGP sync, which people normally need to turn on. Remote LFA is cleaner in the sort of Spring segment routing case compared to LDP, which we'll see in a minute. The other interesting thing is that IP version 6 is built in, so you can allocate a different index for IP version 6 packets versus IP version 4 packets, and so you've got a built-in IP version 6 shortest path forwarding, and so you don't need to use 6PE. Sometimes today people end up using LDP plus 6PE for the IP version 6 traffic, which is a lot messier. So there's several good advantages of using this instead of LDP. The other good reason is that you can combine it with other sorts of segments. You can combine this with adjacency segments and create a sort of hybrid path, which might consist of various sections which are completely nailed down using adjacency labels and other sections which are just shortest path forwarding using these node labels. Another aspect on this node label discussion is, of course, what makes life easier is if each router chooses the same label range. So in the previous example, in general, most of the routers had different label ranges, and you're seeing the label value change hop by hop as a consequence. Here is same diagram from the topology point of view, but this time each router has chosen the same range for its label block, 100 to 199. This gives you a very nice property that in this example where we're forwarding towards router R7, wherever you are in the network, it's always labeled 107 because each router has a label block starting at 100, the index of the destination is 7, so whichever your nearest neighbor router you're sending to, it's always expecting label 107. And so technically it's still a label swap, so from R2's point of view, it's, the forwarding table would say label in equals 107, swap it for label 107 and push it out towards R3. This is very good for troubleshooting, so wherever you are, whichever router you're logging into in the network, if you're looking at routing tables and forwarding tables, if you see label 107, you immediately know this means, shortest path forwarding towards, router R7. And so this is supported in Junos, the ability to configure, consistent label ranges. And so what you'd do in the ISIS or OSPF config is you'd say, okay, the starting value in this example is 1,000, the range is 200, perhaps there's 100 routers in this network. We choose a range of 200 to allow for expansion, in the number of routers. And then we specify the index for this particular router. So this particular router, we're allocating an index of 101 for IP version 4 packets and an index of 11 for IP version 6 packets so that those can be disambiguated. And we're very generous in the range that you can set. So you can set this, these labels can lie anywhere in the range from 16 to 1 million. So that's ample range to be consistent with other vendors and things like that. What I'll do now is I will say a few words about traffic protection. How do we do fast reroute style behavior for this type of traffic? You've probably heard of LFA, where if you've got an adjacent neighbor, link breaks, you send the traffic to an adjacent neighbor. If it's a loop-free alternate neighbor, that means it won't send the packet back to you. It will send it towards the destination, if the IGP metrics are in your favour. Remote LFA is an extension to that, which you can use if LFA doesn't give you coverage. And here's an example of it. So in this diagram, we've got traffic going from R8 to R7. This is segment routed traffic. Let's suppose it's traffic that's using node label forwarding, shortest path forwarding, but the similar principle applies for adjacency labels. And so from the point of view of R1, suppose R1 wants to set up sub 50 millisecond protection in case this link between R1 and R2 fails. So what it needs to do is, first of all, it says to itself, well, have I got a direct LFA neighbor? And it hasn't, because if it were to deflect the packets towards R0, that wouldn't work, because R0 hasn't realized yet that this link has gone down. And so R0 sees 2 ECMP paths towards R7, and so half of the packets would actually end up coming back towards R1, and so you'd end up with a micro loop, in fact. So that wouldn't be doing your fast protection for you. So there's an extension to the scheme known as remote LFA, where R1 defines or identifies a sort of helper node, known as the PQ node, such that if it can get packets to the PQ node, if the IGP metrics are in its favour, then the PQ node is partway towards the destination, and from the PQ node you can also use shortest path forwarding to get to the destination. So in effect it's a trick to get past the fact that R0 would send the packets back towards you. And so the way you get the traffic past R0 is to in fact put it in effect a tunnel that terminates at R4, because from R0's point of view the shortest path towards R4 is this way around the network, which is what we want. And so in fact you end up with two label stack for this protection path. First of all, on top the node label required to reach R4, and then below that the node label that R4 is expecting to reach R7. Now R1, being the point of local repair, knows these label values because they're all communicated in the IGP. It calculates the label values according to the method I described in the previous slide, and so it can successfully work those out, push them onto the packet, and so you achieve sub 50 millisecond protection for your Spring traffic. Now, remote LFA, you can use it for LDP as well, but there is an interesting difference. If this was all LDP, if you replace all of this with LDP labels, then R1 would not know normally what LDP label R4 has allocated for shortest path forwarding towards R7. And so what needs to happen is that a targeted LDP session comes up between R4 and R1 in order to exchange that label value. That's all right in principle, but in a big network you can have a situation where particular nodes, which are perhaps centralized, get targeted by lots of points of local repair as a PQ node, so it can end up with of order hundreds of incoming targeted LDP sessions. So that could cause problems with scaling in a really big network. With Spring it's a lot cleaner because you don't actually have this targeted LDP session, by virtue of the fact that each route in the topology knows what label is needed by any other third-party route in the topology to reach any other final destination router, because all that information is propagated in the IGP. Whereas in the LDP case, that information is only communicated over, what you'd call, sort of private LDP sessions. So if you haven't got an LDP session with a particular router, then you won't know what labels it's expecting. Now you might say, well, okay, that's fine in the topology you showed, but what if I've got a more difficult topology where here the metric's mostly 1, but I've got this really high metric between R4 and R5. In that case, there is no PQ node. There's no nodes that I can sort of identify to help me get the traffic towards the destination. And so that's where another scheme, topology independent LFA, comes in, where we can use an adjacency label as part of the protection path, because we need to get the packet from R4 to R5, but R4 would want to send the packet this way around the network. It doesn't realise that that link's broken, got this really high metric of 50, so R4 would never send it like this. But with the adjacency label, as I mentioned, the adjacency label is a strict forwarding paradigm. So the packet arrives for the adjacency label corresponding to this link. R4 must send the packet on that link. It doesn't matter what the IGP is saying. So that helps us force the packet across this link. And so what R1 would do for this repair action, it would recognize there's no PQ node. It would recognize this. It would recognize that to get the packet round to R7, what it can do is to put that adjacency label as part of that label stack. In fact, it would put the node label for R4 on top, the adjacency label for that link, and finally the node label for the destination that's expected by R5, and so successfully send the packet like that. Now, for link protection, it can be proven that for any topology, as long as on each link you've got the same IGP metric in each direction, so in that case, for example, it's 50 in the direction from R4 to R5 and also from R5 to R4, you need at most only one adjacency label to do the protection. If you want to do node protection, it's more complicated. In fact, the number of labels, in principle could be unbounded for a pathological, topology. But for, adjacency for, link protection, it's actually, just one of these adjacency labels at most to, bridge the gap. So that's a flavour of, Spring and segment routing. What I'll do now is I'll talk about the, sort of NorthStar angle, because, in fact, when you're using segment routing traffic engineering, for most of the use cases, the controller is very important. It's very difficult to, do these use cases without the help of a controller. So I'll say some words about NorthStar principles, and then we'll see how it's applied to Spring and to segment routing. So this is the concept behind NorthStar. So the key thing is it's a SDN controller for the wide area network. It's geared very much to traffic engineering. One of the key attributes of it is that it is a real-time controller as opposed to being a sort of offline tool. So it's got direct visibility of the network through protocols, and so it knows as much of the topology of the network as any of the routers do. In fact, it can know more because it can see across multiple domains, whereas individual routers typically cannot. And so from the network itself, it can see the topology of the network, either via IGP peering or more commonly actually using BGP-LS. I'll say a bit more about that shortly. It can see LSPs that it has placed on the network. It receives requests from a human operator, if you want, via a GUI, and also requests via northbound REST APIs. You can have a higher layer sort of orchestration system, sending NorthStar requests. And in terms of the use cases, one of the key use cases is building traffic engineered paths to meet particular service requirements, and path diversity is a classic example of that. More about that later. Another class of use cases, especially for ISPs with huge volumes of internet traffic, international transit providers, they've got terabits and terabits of traffic. They need to make use of expensive long distance links, make sure that the traffic's sort of spread around the available links in order to squeeze out the maximum resources. And so NorthStar, with its global visibility, can do sort of global optimization of the paths of all the LSPs network-wide to avoid hotspots and to make use of all the link resources. And then also some automation use cases. So, for example, you can tell NorthStar node 128 is going to go down for maintenance at 2 a.m. And so automatically beforehand, the controller would move away all of the affected LSPs. And then afterwards, you can either press a button or you can have a pre-configured end time to the maintenance, at which time NorthStar would move them all back again. So that takes the sort of pain out of preparing for a maintenance window. The other actual, key use case, which we didn't even appreciate when we were first, sort of designing NorthStar, is just the pure visibility, the fact that you can see the path that an LSP follows through the topology. You can go back in history and see the path that it followed 2 weeks ago if you're doing some investigation, which is much easier than looking on individual ingress routers and looking at strings of IP addresses and things like that and trying to correlate it with a network map. So that's a very interesting class of use cases as well, in fact. So NorthStar's been very successful. So one of the sort of flagship deployments, one of the world's biggest telcos is using it in their global MPLS network, where there are of order a few thousand MPLS nodes that are in this topology, and NorthStar's the controller of it. Something that we're adding, which is going to be released actually in a couple of weeks' time, is telemetry. So having the controller the ability to consume streaming telemetry coming from the routers, and that's being used to drive interesting use cases as well. And I'll come back to that towards the end if there's time. So in terms of sort of protocol ingredients that are important for such a controller, PCE, Path Computation Element. This is a protocol that was first designed 10 years ago. It's been augmented a lot in the last couple of years to deal with sort of controller-initiated LSPs as opposed to ones that it's just simply managing that were originally configured on the ingress routers. So in short, what you've got is the path computation element, PCE, and that is the NorthStar controller. And then you've got the path computation clients, the PCCs, which are the individual ingress routers. And so you'll have a PCEP session between the PCE and each of the PCCs. And so what the PCE, NorthStar, is doing is computing paths of LSPs and then sending a PCEP message to the ingress router saying, right, I want you to set up this LSP. This is the precise path that I want you to follow for this LSP, other attributes perhaps, and then the ingress router responds by actually instantiating that LSP on the network and then finally replying to the controller that it has successfully set up the LSP. And then once an LSP is up and running in service, the controller can make changes to it if there's a need to alter the path of the LSP, perhaps in accordance to traffic changes, sort of operations such as maintenance, moving the LSP in order to undergo maintenance on a node, anything like that. Then the controller simply sends a PCEP message to instantiate the change, and the ingress router responds by making the change on the actual network. Another key protocol ingredient, I mentioned this briefly, BGP-LS, BGP link states. So this is a new BGP address family for conveying network topologies in a sort of easily digested form. And so if you've got this network topology, normally you've got traffic engineering extensions, which are still used for conveying topological information and link attributes. So all of the routers in this network would be using the TE extensions. You might have admin groups configured on these links, link colors, you might have SRLGs, you've got metrics. And so all of that information is conveyed by the traffic engineering extensions and can be exported. So you can use just one router as a BGP-LS speaker or two for resilience. Those are exporting that information using TLVs that are defined for this BGP-LS address family, so that the controller knows as much about the topology as these routers do. And so in its mind, it's got real-time sort of replica of the network topology, which allows it to do path computations. It has to know what the real topology is of the network in order to successfully do path computations across that topology. A classic use case for the controller is path diversity. So in this example, we want to have two diverse LSPs, blue one going from PE1 to PE3, red one from PE2 to PE4. Why do people want diverse LSPs? As a replacement for SDH private circuit service, where in the past people would ask their telcos, I want a pair of E1 leased lines, I want a pair of diverse ones. For things like broadcast television, things like real-time market data in the financial world. So in the SDH world, most telcos tell us that when customers order private circuits, 30 or so % of the time they ask for the sort of diverse option. So it's quite a prevalent service. And so people wanted to shut down their SDH networks and offer next-gen replacements based on MPLS pseudowires need to offer this path diversity service. Now the tricky thing is, if you're doing distributed path computation, if it's the individual ingress routers that are computing the paths, then there's no mechanism for them to collaborate in order to make sure the paths are actually diverse. And so what would happen is that in fact PE1 and PE2 would do their path computations independently, and so it's down to luck whether the paths are diverse or not. in this topology, you've got lots of ECMP paths, and more often than not, the two LSPs are going to end up sharing fates. And you can see in the middle of the network, they're actually passing through the same node, and so the path diversity criteria that we set has not been met. Instead, you tell the controller, well, actually, you know, I want these to be diversely computed. It does the path computation simultaneously as a path computation for the two LSPs, and so successfully can create two diverse paths and place them onto the network via the PCEP sessions that it's got with the two ingress routers. Another type of use case actually is different types of cost functions. So by default, the controller would compute the shortest path that meets lowest IGP metric. In this particular topology, we've got two end-to-end paths possible between X and Y in terms of equal IGP metrics. We could set up two LSPs and load balance traffic across those two LSPs if we wanted to. But there might be a subset of customers of this network who absolutely want the lowest latency path. And so here, if we look at latency rather than IGP metrics, in fact, you can see that if we take the north side path from X to Y, that's got lower latency than the south side path. So if you've got customers who particularly want lowest latency, you can map them onto this sort of premium, sort of engineered path. They might ask, how does NorthStar know what the latency of a link is? And I'll come back to that in a little bit. So now let's talk about NorthStar and segment routing for the traffic engineering. So NorthStar up until now has supported RSVP LSPs for the traffic engineering. And so in the PCEP session, it in effect is saying, I want you to set up an RSVP LSP to the ingress router. The RSVP LSP gets signaled by the ingress router through the network in response to that, PCEP message. But now, in fact, in a couple of weeks, we're going to release NorthStar 3.0, which will also allow you to set up segment-routed traffic engineered LSPs. I mean, from the path computation point of view, actually, it's, the same. I guess when NorthStar's doing a path computation, it doesn't matter whether finally the LSP is going to be a segment-routed one or an RSVP one. And you can choose, when you set it up. So in the dialog box, there's a pull-down box. You choose RSVP or you choose segment routing, depending on what you want to set up. Additional ingredients that are needed to support segment-routed LSPs. There's, first of all, from the topology point of view, as well as needing to know the sort of layout of the links and nodes and IGP metrics, NorthStar needs to know the adjacency labels associated with each link. We talked about adjacency labels. NorthStar needs to know those. Also node labels, because NorthStar can also deal with node labels as well. And so those are conveyed to NorthStar either via ISIS peering or via BGPLS. And so there's a draft that we wrote which are BGPLS extensions to segment routing to allow the adjacency labels and so on to be conveyed on the BGPLS session. So it's the same BGPLS session that we talked about before, but carrying some extra info in terms of these labels. And then from the PCEP point of view, there's a new PCEP capability, and so the two parties, the PCE and the PCC, when the session first comes up for negotiates, they say, okay, we've got this capability, and so that allows segment-routed LSPs to be conveyed over the PCEP session. So by way of example, here's a topology. In these blue, well, not blue, it's sort of orange colour actually, these sort of arrows, they're showing the adjacency label that's been allocated by the router in each direction for each adjacency. NorthStar can see those through the BGPLS session. And so you might say to NorthStar, okay, give me the green LSP, I want an LSP between R1 and R8. Perhaps it needs to have a particular bandwidth allocation to it. Perhaps you say, I want 500 megs allocated to this LSP. NorthStar does a path computation and finds the shortest path that can meet 500 megs of bandwidth requirements. NorthStar then conveys via the PSEP session the request to the ingress router to actually install this LSP. And in so doing, the controller's actually conveying the value of each label in the stack that must be sort of installed in the fib of R1. And so, in fact, in this example, that label stack would be 406, 607, 708. And so the instructions in the PSEP message would be, first of all, push the packet towards R4 and also, have this label stack on the packets. And R1 receiving that PSEP message, installs that in its fib. And so, traffic going to R8 would follow that, traffic engineered path that's been, computed by the controller and installed in the network. An interesting point to bear in mind, if indeed you do need bandwidth assignments for your LSPs, then it's mandatory to use a controller because there's no mechanism with Spring segment routing for reserving bandwidth at the network layer. It's a bit different from RSVP, because with RSVP you actually reserve the bandwidth at the network layer, and so you could have a LSP that's computed by the ingress router without the help of the controller with a bandwidth reservation. In this case, you must have the controller, because what the controller does is it keeps track of the bandwidth in its own mind. It has created all of these LSPs. It remembers the ones that it's created before, remembers how much bandwidth the operator would be requesting to put on that LSP. And so in its mind, when it has its topology map, it decrements the remaining bandwidth on a link according to what Spring LSPs it's already set up across the link and the bandwidth that had been allocated to those. So it's all self-consistent in the mind of NorthStar in order that we can get away without having to explicitly reserve bandwidth at the network layer. So here's a little bit about the sort of nuts and bolts, expanding on what I just mentioned. So this is the sort of segment routing capability, TLV, that gets exchanged at session bring up. If both parties actually convey this, then in fact the session is ready for carrying these segment routing requests over the PSEP session. The other thing that's negotiated actually is the number of labels. So the ingress router needs to tell the controller how many labels it's capable of coping with in terms of the number of labels it can push onto a packet, in terms of its forwarding capabilities, because different routers out there from different vendors have different capabilities in terms of how many labels they can have in a label stack. And so it's the job of the controller to bear that in mind and not attempt to push a label stack via the PSEP session onto an ingress router that's greater than the amounts that that router can cope with. So you've got this TLV to deal with that aspect. And so in fact, for NorthStar in this upcoming release in a couple of weeks, the actual underlying use cases are very similar to what we support for RSVP traffic engineering, constrained path computation, taking into account admin groups or colors, taking into account bandwidth requirements, taking into account path diversity requirements, which could be link diverse or node diverse or SRLG diverse, maintenance mode, which we talked about, bandwidth calendaring, so setting up an LSP not now but at some time in the future. I want this LSP to come alive at midnight on Thursday night next week, something like that. You can do all of that, whether it's RSVP or Spring traffic engineered LSPs. The other aspect is that in the example I showed a path that was consisting of a stack of adjacency labels, so the entire path was completely nailed down. You can also have paths where sections of the path are just defined by node labels, which would be a shortest path forwarding. So there might be a case where you only want to strictly traffic engineering the packet flow across a certain part of the network, perhaps where there's a bottleneck, and you don't mind how it gets from that section to the final destination node. And so you could have a mixture of adjacency labels and node labels in the label stack, and so NorthStar can deal with that type of use case as well. So this is coming very soon, so if you want to get involved, do a trial of it, please let us know. I'll say a few final words. I'm going to keep an eye on the time. We've got a few minutes left. I'll talk about something else we're adding to NorthStar as well, which is relating to telemetry. So that will help NorthStar know even more about what's happening in the network, and that leads to some interesting additional use cases. And it was inspired by things like aircraft engines. So aircraft engines, they're sort of primitive in that they're sort of mechanical devices, but they actually stream out tons of telemetry. In fact, over the airwaves, to the engine manufacturer, while the plane's in flight, things like pressure and temperature and vibration readings and rotor speed and all that sort of thing. And so in tribute to that, we've introduced telemetry onto our routers, and we actually call it a sensor, in tribute to these physical sensors that exist on the aero engines. And so you can have sensors for things like interface statistics and queue statistics and LSP statistics and memory utilization and fib utilization and optics info, all sorts of things. And this is in contrast to SNMP. So in the past, SNMP was used to gather this type of info. With SNMP, it's very much a sort of request and reply paradigm. And so if you want all of your interface stats and LSP stats, you might be collecting them every 10 minutes. The collector needs to ask what information it wants via SNMP OIDs. That arrives at the routing engine of the router, and then the routing engine needs to gather that information, construct SNMP packets, and send them by way of reply. And then 10 minutes later, the collector asks exactly the same sort of questions again, exactly the same OIDs, it sends again, and then 10 minutes later, and so on, which is quite inefficient. With the streaming telemetry, in contrast, you're telling the router up front as a one-time operation what info you're interested in and how often. And from then on, it's just streaming it proactively towards the collector. And furthermore, if it's information that's collected on the line cards, so this is things like interface stats and LSP stats, then those telemetry reporting packets are actually constructed on the line card and sent directly to the collector, so they don't have to go upstairs through the control plane. So these factors lend itself to having really high frequency telemetry if you want to. I mean, this is a sort of somewhat exaggerated example where this is looking at interface stats. This is 30 seconds per division. You might be able to see these grid lines. That's 30 seconds. Individual reports are separated by 2 seconds. Every 2 seconds, the router's sending telemetry saying what's the interface stats on this interface. The green is one direction, the yellow is the other direction. In the yellow direction, there's no traffic. But what we're doing in the green direction, we're sending really short-lived spikes from a traffic generator, and those are being resolved. If it was SNMP, where you're polling every 10 minutes with averaging, then of course those spikes would be washed out into just a flat line, which would be the average of the mark space ratio. But here we're resolving, these very short-lived spikes. Similarly for LSP statistics, so this is how much traffic on each LSP. Again, 2 seconds between each data point, so we're picking out these very fine-grained structures. So what we're doing here on the traffic generator is just winding up and down the traffic level on the slider and just, making the traffic change, with quite fine-grained structure. And so what we're adding to NorthStar is the ability to consume such stats. Now, in the NorthStar case, of course, we wouldn't want NorthStar to react on a sort of 1 or 2 second timescale. That would be causing too much churn. And so in the NorthStar case, we average to 1 minute intervals. So NorthStar's operating on 1 minute averages in the use cases that I'll talk about. And the information that we're sending, in fact, from the network is how much traffic is traveling on each LSP, as reported by the ingress router, how much traffic is traveling on each physical link, and also link latency. And so you can have a do-not feature known as RPM, measuring the latency of links between adjacent routers, using hardware timestamps. And so that link latency is reported to the controller as well. And so that lends itself to interesting use cases. From the pure visualization point of view, what you get is heat maps. So you can have a heat map, you're looking at the topology of the network in the GUI. The topology itself has been acquired via BGPLS as discussed. And now these links are color-coded according to the reported streaming telemetry stats for each link. And so you can see color-coded what the utilization is. And so you can see at a glance that this link is rather congested. These ones are moderate, and the ones in the top right are fairly quiet in comparison. This is a screenshot from the actual GUI, and so as well as showing colours, it actually reports the percentages. This is the percentage traffic load in each direction. So you can see in this case it's about 75% in each direction between these two routers. And also you can drill down, so whether it's a link or an LSP, you can drill down on an individual entity and see bits per second as a function of time, packets per second as a function of time, delay as a function of time, all of this coming streaming from the respective ingress routers. And in a similar vein for latency, you can see a heat map, what's the latency of each link, reported in microseconds with color coding, according to how big or small the latency is. So that's visualization, so that's very useful in itself. But where it becomes even more useful is actually having automated actions in accordance with the info that you're receiving. So this is getting towards self-driving networks, step towards this self-driving paradigm. Here's one example. Based on link utilization, you can say to NorthStar, suppose a link anywhere in the network is more than 80% loaded. You can have NorthStar automatically move away LSPs from the congested link in order to ease the congestion. And NorthStar can do that because it knows how much traffic is traveling on each LSP, because it's receiving that information from the streaming telemetry as well. And so it can work out which LSPs to move away. Here's an example. So this red link is the congested one. You've got these various LSPs going across it. NorthStar works out that if it moves this one away, it will successfully ease the congestion. So it sends a PSET message to the ingress router, gets it to move it away, it's eased the congestion, it's spread the LSPs around the network. Sometimes people do this manually, and that can be quite tricky. So if you're doing it manually, you need to realise that a particular link's congested, you need to look at the LSPs passing across it, you need to work out which one or which ones to move away, you need to log into the ingress routers of those LSPs that you're moving, you need to put something in the path, the RO, to make the packets move away. Maybe you put some loose hops or strict hops. It's pretty involved. And what can happen is you can end up in a situation where, if you've been doing this sort of thing for several months, you end up with lots of LSPs which have been pinned around the network in different ways to ease congestion around various hotspots. But then, the traffic might have changed, and so you look at an LSP and you think, well, why is this LSP pinned round like this? Why did we do that? And then you think, well, if I unpin it and let it follow the shortest path, is it going to cause problems? Am I going to cause congestion? So it's much better to have an automated system that can do path computation of the whole set of LSPs in its mind very easily and work out where to place LSPs accordingly. Another use case based on delay. This comes up a lot, especially from people who run global networks. Perhaps they're renting transmission capacity from different WAN providers. And so suppose we've got this operator, they're renting capacity from one provider X, from one provider Y. They want the lowest possible latency LSP from PE1 to PE2, perhaps it's carrying sensitive market data traffic or something like that. NorthStar knows what the latency of each link is through the telemetry reporting, and so you can ask it to compute the lowest latency path from PE1 to PE2 at the other side, And at the moment, you can see that this is the lowest latency path. So of these latencies, the dominant one is the ones across the WAN. These are all local links, so they've got very small latencies. You've got 11 here across the WAN compared to 19 up there, so this is the shortest path. Now, what can sometimes happen is that you get step change in latency. Within this WAN provider Y, there might be a fiber cut, it might be a transatlantic fiber cut. The latency jumps up because we're on a longer protection path. Now, the customer of WAN provider Y, who owns this MPLS network, doesn't explicitly get a notification straight away that the fiber's been cut, but NorthStar sees the change in the latency, and so it automatically redoes the path computation, sees if there's a shorter path. And in this case, the latency has jumped from 11 to 23, and so in fact the north side path is the lower latency. So it moves the LSP, it sends a PSEP message to the ingress router, telling the ingress router to move the LSP as shown here, and it does it in a make before break manner. So in the forwarding plane, you don't see any interruption to the flow of packets. That happens, in a seamless way. Again, people, in the past have been trying to do this manually. So it means, first of all, they have to realize that the latency's gone up. They have to, sort of think, okay, is there a shorter latency path? They need to put a ERO on the ingress router. They have to go into the CLI to do this. Having it automated makes it a lot easier, of course. Then the final slide, actually, this is getting more towards capacity planning. What we want to get into is predictive capacity planning. On NorthStar, you can do capacity planning. You can take a snapshot of the network, import it into a sandbox, do planning, like you could say, okay, bump up the traffic by 50% to see what happens over the next year. Can I still successfully route that increased traffic growth? With this telemetry, you can take a snapshot of the network of what was the busiest hours. You could say to NorthStar, open up the planner with the traffic stats that you've collected from the network corresponding to the busiest hour that you've observed, and you can use that as your baseline. But what we want to get into is predictive capacity planning, where, in fact, the controller is doing the capacity planning in its own mind on a sort of quasi-continuous basis. It's looking at the traffic volumes as a function of time, it's extrapolating, and then it would tell you, hey, in 8 months' time, the network is going to go from this situation where the loading's okay to this situation. So wherever I put the LSPs, wherever I try to reroute them, I'm still going to have these hotspots. You better, consider, upgrading the capacity. So that's a flavour of what we've been doing with traffic engineering recently. So we've talked about, Spring and segment routing, how that lends itself to traffic engineering. We've talked about NorthStar and how that's a key ingredient for many traffic engineering use cases, and how we are augmenting the use cases, getting more towards self-driving networks by virtue of the streaming telemetry. So thanks a lot for your attention.
Thanks a lot, Julian.
Okay, pleasure.